Thanks for the organizers to having me here. It's a wonderful place. And today I'm going to tell you, so these are going to be two lectures linked to each other. The first chapter is going to be about turbulence. The second one about shocks. And so I'm Pierre Lesaffre. I don't know much about turbulence, as you will see, but fortunately, I'm not the only one, since we know so little. I'm going to give you a small introduction, introduce you Reynolds numbers, the energy cascade, the first correction to the energy cascade by Kolmogorov, and maybe if I have time, I will give you a small lecture on intermittency. And only at the end, so I'm sorry for the ones who are looking for very advanced topics in turbulence, I will give hints on how to find your way into more advanced topics, MHD turbulence and stuff like this, okay? I will keep the lecture very, very simple, I hope. And so I wish to proceed with the first part, and then we'll do 15 minutes questions, okay? So what is turbulence? Well, I don't really know. So this shows how the organizers are so bad at choosing speakers. But I'm not the only one. And so the word turbulence, in fact, comes from, it was coined by Leonardo da Vinci. He was walking next to a river and he put a stick into the river and looked at the whirlpools forming. And it comes from the Latin. This was taught to me by Marie Farge a while ago, so I'm not exactly sure how whether it's true or not. The Italian speakers in the room will correct me. But turbula in Latin means a crowd, but a small chaotic crowd, okay? And a random crowd. And turbo in Latin means a whirlpool, okay? So he thought this mixed together is a good expression of what he was seeing. And so what you are seeing here is smoke developing whirlpools in the wind. And what are you doing, Jérôme? And you can recognize with your eyes that this is, there are characteristic shapes. You want to go back here. What are you doing? So I need to share again, right? I want to put my camera on. Okay. Okay, that's coming back. Except now you see me here, so I need to do this, right? No, yeah, you have to do it. You're the master on this side, okay. So turbulence is a mixture of random chaos and very recognizable structures. And for the time being, what I'm going to teach you today is much more about the randomness of these things than the coherent structure. This will be for the second part because the organizers were clever enough to assign me shocks and turbulence in 2 hours. So let's go. Okay. So what do we know about turbulence? Very little. This is only one slide. These are the statistical properties of turbulence as we know today. The Sporer spectrum, we're going to go in details through this. You don't have to read it, but it's mostly Kolmogorov's legacy. Okay, he's almost single-handedly, he found almost all the properties of turbulence as we know them today. Before I delve into the realm of turbulence, I have to introduce you to a tool, a very simple tool, which was designed first by people who wanted to extract the contours in pictures. So they, instead of looking at the blend image like this, they decided to take the differences between neighboring pixels. In other words, they were taking they were taking 2 points at given positions, separated by a given distance, a lag, L, and they take the difference between the field they are looking, whether it's a scalar or a vector, we'll see later, and they just take the difference. And this they call increments of the quantity X at a given lag, L, okay? I'm not sure I'm gonna use this a lot. You can do several types of increments. You can first, this looks a bit like a gradient, okay? You can define increments of vectors, and then you would project the difference of vectors onto either the line separating the 2 points or the orthogonal direction separating the 2 points. You can, so I said about the gradients, and all this also you can take convolution with a wavelet like this, which would take a positive weight at some point and a negative weight at some point, with some averaging around these points, which is nice when you have noise in your images. So various type of increments. And now you know what they are. Okay. Now let's look at the equations of fluid dynamics for incompressible fluids first. I don't want you to actually read this equation. I'm gonna delve into this in the second part of the talk. In this part, we only need to deal about dimensions, and so we have here a velocity, a time, so we can describe everything with 2 dimension numbers. A typical velocity, which I'll call delta U, because you don't care about, everything is Galilean invariant, so you don't care about the fluid, the average fluid motion. What you care about is the difference, the increment at large scales, the difference in velocities, the typical difference in velocities at the largest scales, okay? And the typical length scale. And then you have the viscosity in this equation. And if you take the ratio, the only dimensionless ratio between these 2 numbers, you build the Reynolds number. And now your equation is much simpler, and it's parameterized only by 1 dimensionless number, the Reynolds number. So what are these numbers? Oh no, maybe I forgot about this slide, okay. Depending on this number, you have very different behaviors, but the fluid behaviors depends only on this number. That's the key point. So if the Reynolds number is very small, around 1, you get a laminar, very predictive, even steady state regime. And here on this picture, you see, no, this is not working. This is working maybe, because the mouse is on the other side. Yes. So here you have an obstacle. Fluid is moving this way, and students at PSL who made these videos, which you can download here, drop some dye here, and here you have a steady state and here a steady state. And here, when you increase the velocity of this, you increase the Reynolds number because the delta U is increasing. And you start to observe a periodic behavior, okay? You have whirlpools on one side, on the other side, on one side, on the other side. But still this is periodic, so kind of predictable. When you increase the velocity still, then you get something which is completely chaotic, and that's where you get developed turbulence, and that's the regime in which we are going to focus in this lecture. So how does this apply to the interstellar matter? This is my way of describing the interstellar matter cycle in a temperature density diagram, where I put all the various phases, various typical gases you can find in the galaxy, okay? So let's say you start from the very hot ionized medium at 1,000,000 degrees. This is going to cool down at almost a constant pressure into WNM, diffuse gas, whether it's cold or molecular and dense. Then at some given point, gravity takes over and you have collapse and formation of stars with photospheres and disks. And when the stars are born, they launch jets which replenish this gas. And at the end of their life, sometimes they explode in supernovae, which leads to giant bubbles of hot ionized medium. So in these various phases, you can find typical velocities observationally. You can find typical length scales, and using physics like Spitzer to estimate the viscosity, you can build Reynolds numbers. That's what I did in this. So you recognize the various phases I just told you about. And this is the Reynolds numbers of these phases. So you can see that you get almost to the periodic case in the hot ionized medium, but most of the time you are very turbulent in the ISM. You can build other types of Reynolds numbers, which has the magnetized Reynolds number, when instead of the viscosity, you take the resistivity, and instead of the velocity, the Alfvén speed built from the magnetic field. And you have some kind of ambipolar diffusion. I won't talk much about this, but these are the typical Reynolds numbers you can find in the ISM. Let's go now to the Kolmogorov cascade. So Kolmogorov imagined that there is some ordering in this chaotic behavior of the whirlpools. You inject energy usually at the larger scales, and then through compression of vortices or stretching of vortices, you will get an energy flow down to the smaller scales, where you will get the dissipation, okay? Because that number nu is usually very small compared to the delta U and L here. So you need to bring the energy at much smaller scales so that the delta U over L becomes comparable to the rest, okay? And so the first idea is that you assume steady state. That means the injection rate is going to be equal to the dissipation rate at the other end of the cascade. And so the transfer rate across all these scales will always be of the order epsilon, okay? So let's go a bit through the demonstration of the Kolmogorov spectrum, but this is a light version. You can read the paper. It's much more technical with statistical tools. So let's say at a given scale L now, in between those two injection and dissipation scales, now the typical scale, the typical velocity from this dissipation, from this pi number and the typical L you can build is like this from dimension reasons. That's the only velocity-wise number that you can build from epsilon and L. So that's going to be the typical velocity at this scale, and you can also build the typical Reynolds number at this end. Well, no, I'm just saying shit. Sorry. Let me go back to here. This is just expressing that the local pi L rate is constant and equal to epsilon. Okay. UL cube over little l has to be a constant equals to epsilon. So then you get UL. And now you can build the Reynolds number. And this Reynolds number at this scale will define what kind of flow you have at this scale. So that's the idea. You can now write the increments of the velocity as this typical scale that you built. This is now a dimensionless scale, which depends on the dimensionless number, the Reynolds number at scale L. And now what Kolmogorov imagined is that if you have a very large intermediate Reynolds number, then this is going to be universal. As this typical, the statistics of these increments are going to not depend anymore on the Reynolds when you put the Reynolds very large. Okay, and this is the key idea. If you do that, then it means the average of these things, of the increments to the power p, are going to be simply this universal function to the power p times ul to the power p, which means epsilon p to the 3, lp to the 3. So this is going to be proportional to lp to the 3, okay? And in particular, if you take the second power here, you get delta LU square that behaves as L to the 2/3. And if you now try to relate this to the power spectrum, which is the energy for velocity in a defined bin of wave number dk, then from this integral, you will see that you need to derivate this one in order by k, which is the inverse of L, to get to ek. So from this, you derive the -5/3 for the energy spectrum of the velocity. Okay, so that's the first result on turbulence. So I resume here. I summarize again the assumptions, which just when we went just through. So the energy transfer rate pi L is constant at all scales. That means the velocity increments depend only on the local Reynolds number Re of L. If the turbulence is homogeneous and isotropic, and you put the Reynolds number to infinity, that means the scales are way above dissipation. So in other words, we are in the inertial range. Then you get this power spectrum, delta L of U square is proportional to L to the 2/3. And you get this E of K proportional to K to the -5/3. If you now use this scaling that we just found out, and you try to state the scale at which the Reynolds number is of order 1, in other words, this is a proxy, a way to define the scale at which the dissipation will be very, very large, then you will find that the dissipation length scale is proportional to this, okay? And this is called the Kolmogorov length scale. So let's see now how this behaves in our galaxy. So this is data compiled by Edith Valgaron. And what she did is to look at molecular clouds and their typical velocities versus scale. And so there are lots of measurements. And if they were behaving like Kolmogorov, they would follow this kind of slope, okay? So you see that it kind of deviates here. And above, you have a scaling which is rather like Burger's. So Burger's is just using shocks. If you have a discontinuity in a power spectrum, maybe you know that you have Gibbs phenomena. And so whenever you have, even if you take the power spectrum of a single shock, a velocity jump in a way, you will find a K to the -2 spectrum. This is just because the Fourier spectrum generates Gibbs phenomenon to generate a jump. Fourier likes continuous stuff, and you're giving it a jump. So you get K to the -2. And this is called Burger's turbulence when you have lots of random discontinuities, basically. So at large scales and maybe at large velocities, maybe when the scale here, when the velocity here becomes supersonic, you change the behavior. And this has been checked in incompressible turbulence simulations. There is a very impressive 10,000 cube isothermal simulation done by Christopher Federat, where he finds, so you're now looking at almost exactly the same thing, but it's just the Mach number. So it's the delta U over C. And when the Mach number is on order 1, this is this position. And above it, you have Burger's scaling. Below it, you have K41 scaling. But unfortunately, our galaxy is slightly more complicated. If you look here at a picture of the galactic plane, you can imagine that you have gravity and supersonic turbulence in this plane. And there's an ingredient which enters into play, of which we have been able to take a very nice probe since we have these Planck images. It's the magnetic field. And so the turbulence, the real turbulence in the ISM is magnetized supersonic turbulence or transsonic turbulence. which makes it even more complicated. Okay. Nevertheless, you can try to look at, for instance, dust images. And if you take several dust images at various scales, you will find that their power spectra align. Now it's the power spectrum of the column density of the dust. Okay. It seems there is a universal slope for the dust, for the column density of dust power spectrum. And I've tried to look in the literature for a link. I haven't found, but maybe some of you know. I don't know whether this has a theoretical ground. Do we know whether this k to the minus 2.9 or 3, the minus 3, is linked to the power spectrum of the velocity? I don't know, but it's nice that we still find a power law, okay? And we find a power law, but still no sign of dissipation. The dissipation scale is probably way below, okay? If you take the dissipation scale, I think you find a few AUs. Let me go back to here. I forgot to say one thing, which is the estimate from this. If you would put Kolmogorov, a few Kolmogorov scalings through this, you would find that the injection rate is between 0.1 and 10 in the CGS. Okay, this is going to be, I'm going to try and explain this and failing miserably. Spoiler alert, in the second part. So let's go back to the last piece of evidence in our ISM for power laws in the sky. This is a nice paper by Armstrong, which is looking at ionized gas. And what you are looking here, what you are looking at here, is a nice power law from several different probes, where it's linked to the ISM here. Now, and the smallest scales are here. You're nearly at the size of the sun, about here. And now you have this minus 11/3 scaling law, but it's because you're not looking at the power spectrum. It's not the total energy in a corona of with decay. It's now the actual magnitude of the Fourier coefficient, and it's slightly different. So be aware of this difference in slope. So if you look at the total energy spectrum, this is the energy in corona at a given size k with a width decay. Okay, and this is the magnitude of the Fourier coefficients themselves. So you have this 4 pi k2 in 3D factor. You would have just pi k in 2D. Okay. So MHD turbulence, I'm not going to give you a lecture on this, but for you to know, there's reduced MHD, incompressible MHD, compressible MHD, isothermal MHD, ideal versus non-ideal, MHD with ambipolar diffusion, whole MHD, lots of various kinds of MHD. For which we have no idea of the scalings, because even for normal ideal MHD or resistive and viscous MHD, I should say, we have a conflicting, these two independent papers tried the same recipe as Kolmogorov, and one of them finds for the isotropic spectrum k to the minus 3 half, sorry, and the other one minus 5/3 for the fluctuations orthogonal to the B field. And there have been a lot of debate around these things. Some people saying that there's no universality in MHD. Some people saying my simulations are better than yours. When in fact there's not much difference. This is minus 1.5, this is minus 1.666, okay? So, but for theories, it's very important. So, Alex Chekoshihin recently wrote a very nice review, but slightly long to read, which reconciles both scalings, and apparently the key would be the orientation of the typical coherent structures found in MHD. compressible MHD turbulence, there is only one paper which we will come back to at the end, which gives an analytical result, so that's nice. 2D turbulence, because if you look at the galaxy from far away and at distances larger than 100 parsec, then this is simply 2D hydrodynamics, in fact, okay? And so it's important to know that in 2D, we don't have energy transfer towards the smallest scales. If you play the same game as Kolmogorov, as Krishnan did in this 65 paper, you will find 2 cascades instead of only 1, and the energy cascade is going the other way. So if you inject energy at this scale, you will find a buildup of a spectrum here, which has the same scaling as Kolmogorov because it's an energy transfer. So you start with epsilon is constant through the scales, and you will find exactly the same thing, except the sign of the energy transfer goes the other way. And if you go look at the vorticity transfer, entropy transfer, the square of the vorticity, you will find that it's going the normal way, but then the scaling is k to the -3. Okay, so applications is, so there's not only galaxies, but disks as well are nearly 2D. Atmospheres, the atmosphere of the Earth, with these big cyclones, okay, which build up from small scales and can take huge, this is because the energy cascade goes the other way, that we get these big cyclones. And also maybe Jupiter, this big spot is often cited as an example, even though we don't really know. So let's go now to the next, to a correction to the Kolmogorov 41, because this was a famous paper by Kolmogorov in 41 paper. So Lev Landau objected that if you look at this picture and at a given scale L, some places have experience very different dissipation rate, transfer rate, okay? In the previous picture, I assumed that the transfer rate, the epsilon L at a given, or the pi L at a given scale is homogeneous. Everywhere it's the same, okay? But now Lev Landau is telling you, well, maybe it's not a good approximation. And in experimental data, we see that this is actually changing very strongly. Actually, they had measured that the statistics of this thing were rather log normal, and they found also that the properties of this log normal distribution was changing with rules versus scales. So Kolmogorov, again him, 20 years after his first paper, designed a new set of hypotheses, which included the variation, the possibility that this transfer rate was varying in space. And so the argument is very close to the previous one. You also define the Reynolds number at a given scale like this. You also divide the typical increments by this velocity that the only velocity you can make from this epsilon L and L, okay? And now, instead of assuming that this is a uniform constant at L, you assume that it has some spread, okay? In other words, the dissipation rate is intermittent. It's not homogeneous. It has strong variation sometimes, but the average of it behaves like the previous epsilon. It's always the same at every scale. If you average over your domain, the local dissipation at a given L, you always find the same value, and you assume this steady state property, and so it's always constant in time. But it has variation over space, and so even though it's the same mean, it can have very strong fluctuations in some places, okay? And it has this specific scaling with L, the average, so the sigma square of this log epsilon. So we assume that log epsilon is a Gaussian, and its mean is behaving like this. And this is just because they looked at it in experiments at the time, and I'm not sure there's more, or maybe Kolmogorov had the intuition that this was going to be the case, or maybe because it's mathematically good, well behaved. Okay, I'm not exactly sure why he postulated this. And when you do this, then when you take the, like before, we want to compute the delta, the increments to a certain power p. What you find is that this epsilon n to the power p, because of the scaling, is going to be proportional to L over big L times this constant b, p to the square. Okay. And so since delta UL is simply this UL times a universal velocity, we still assume that we are well within the inertial range. So the local Reynolds number is very large. Then you can compute this, the average of at a given power, as we did before. And we'll find that now the scaling is not simply p to the third, but there's an additional correction, which makes this thing a polynomial of order 2. Okay, so people started to build this huge apparatus of structure functions, saying that we are going to characterize the statistics of a given field by looking at the successive powers of the increments and how they behave when L is in the inertial range. So basically for us, when L goes to 0. And so this means L is going to, if it has really a power law behavior, is going to scale to a certain power. And we call this zeta of P the intermittency exponent. And so under the log normal model, zeta of P is simply P 1/3 minus BP to divided by 9. Okay. Can we have proofs of this in the ISM, that we have deviations from the original scaling by Kolmogorov? The answer is yes. And so this is what Pierre Leblanc and Edith and Jérôme did at the time. So they look at CO emission in this cloud, which is the Polaris cloud. And instead of looking, here you have the total intensity of CO, but instead of looking at the total intensity, you're now looking at the first moment of the velocity. So you add a V here, and you look at the first moment of your lines, and now you will build an average radial velocity at every point of your map. Okay, so now instead of having a map of intensities, you have a map of velocities going towards or away from you. And now you can do the increments on these velocities. Okay, so here is the map of the increments at a lag of 60 seconds, and exactly 60 seconds, and exactly like in the first image of the Montmartre I showed you. Do you now emphasize places where you have a strong velocity gradient? Okay. And if I swap back between the intensity and the velocity, you can see that. And I know what I showed you for the increments is for velocity in 3D, incompressible turbulence. But why not look at the projections of some things and play the same game of the structure functions? So that's what they did. They looked at the statistics of these increments, which you see here for various lags. And from various lags, they can now build the average of the increments to some power. They have all the probabilities. And they look at how the structure function built on these projections is behaving with respect to scale. Okay, and they can find intermittency exponents. And so I'm now showing you the results. Maybe I will zoom on one case. So this is the results of this paper, the 2008 paper, where you see the Polaris data and the torus data. Torus is as these ones, and Polaris plus signs. And you see overlaid with it is the same thing. I did the same thing on MHD isothermal simulations projections. And and it seems to, for one of them, it seems to lie okay. If you look at other cases, it's not exactly on the same things, but it's still in between Polaris and Taurus. So this is a promising sign that these two things fit. But remember, we're not doing physics anymore. Okay, we are far from the case of homogeneous, incompressible turbulence. In 3D, we are not doing projections of this. So this is more a tool to characterize statistics of an image, say. And maybe it's a good tool. Maybe it's really saying that simulations and observations agree between each other. Maybe it's not a tool which characterizes very well the simulation. So this is just a word of caution. I have 10 minutes left. Do I go through this or not? I hesitate. Okay, maybe yes. So a small lecture within the lecture on intermittency. Here you see the book of Uriel Frisch, who is really the father of all these tools built to characterize intermittency. And here you see the drawings of Leonardo da Vinci on the cover of his book. So I've showed you the PDFs of the increments. This is now a simulation of incompressible hydrodynamic turbulence, in which they look at the longitudinal, so that means projected on the lag velocities, increments. And you see that at large scales, they are pretty much Gaussian. And when you go towards small scales, they develop large wings over the Gaussian, which means there is more probability to have a strong jump, okay, in velocity. Large deviations of the velocity are not as rare as the Gaussian at small lags. In other words, you develop non-Gaussianities towards small lags. So that's the first picture of intermittency. You look at the PDFs of the increments. But remember, this graph is scaled by the standard deviation of the increments. So we don't know from this graph alone how this behaves with the lag, okay? And this is more related to the power spectrum, in fact. So we have filtered out something from this vision. Second vision, it's the vision, the structure function, which I just told you about. This is now data from a wind tunnel in Modane, where they have a probe at given distances, and they look at the evolution of the velocity of the wind. And you can now take the increments of that velocity across this thing and compute the intermittency exponents. And here they are, the intermittency exponents versus the order of the structure function. And you can see they are not a straight line. In other words, they deviate from the Kolmogorov exponent. This is Kolmogorov K41 scaling. Okay, everything is on the linear slope, on the linear curve. And this is the only analytical result we know in turbulence, which is one of the reasons why we use this tool, because we have at least one point where we know we have to be there. Well, for longitudinal signed increments, homogeneous statistical, well, you see where I'm coming. If you look at this at a zoom around 0 and 1 here, you will find the second order structure exponent, which tells you about the Kolmogorov power spectrum. And now, because we are not exactly on a straight line, this is not scaling as two-thirds here. There is a small correction. And so, as I told you before, the energy power spectrum is not exactly 5/3 in this picture. And there should be deviations, and some people have claimed to find them, even though it's very hard because it's small, okay? Next, and I'm losing the, okay. This is probably Benjamin throwing it on the floor this morning. The last one is a bit more technical, but it's just, this is the multifractal spectrum. And it's the way the scaling exponents, look at the places where the increments behave as L to the power alpha. And now these places form part of the volume, and you look at the fractal dimension of that volume. It's very indirect, and it's a bit convoluted way of looking at things. You should rather look at this plot as a scaling functions, which tells you how to move from one of the PDFs I showed you before to the next one. Okay, it's much easier to understand like this. In any case, the three visions are all equivalent to the modulo. Sometimes you're losing the intercept. Sometimes you're losing the power spectrum as in the first view because you divide by it. Here, you're not looking at the constant here in front. You're looking only at the exponent, so you're losing that information. But if you had it, you could go back and forth between all the visions. So each view focuses on a slightly different aspect of intermittency. They're not quite equivalent. But one point I want to emphasize is that none of them strongly constrains the shape of the dissipation structures. And this we know since we have done generative models of turbulence. But before I show you these, I just want to show you a variety of intermittency models, okay, which are around. After Kolmogorov had his, there were a plethora of models which you can try to fit to experiments. And I don't think there is one which is really going much better than the original log normal model of Kolmogorov. So generative models, what are they? The objective is to generate a random field, which will have some of the properties we know about turbulence. So we want the proper power spectrum. We want the intermittency property. And we also want something I haven't told you again, yet, but which is a slight deviation from a slight asymmetry in the third order function of the velocity with longitudinal increments, which tells you in which way we go. Is energy transferred towards the small scales or the large scales, okay? So recently there have been attempts. So the first to achieve this was Chevillard, which was on the previous slide, on the two slides before. And we extended his work for MHD. So here now you have a field, which is, you can turn buttons and have fields which have larger structures or larger injection scales. All these have the same power spectrum, but you can also play with the slope of the power spectrum. You can play with the intermittency curve. All these, so this is fun, but it misses one key ingredient, which is the coherent structures. When you look at these fields, it's not very clear that you find well-defined sheets. And this is an example of a MHD simulation where you find the dissipation lies on very well-defined sheets, okay? This is lost by these generative models, but we are trying to get better. And so right now it's a bit artificial. We're just building new models from random sheets and trying to get all the properties of the intermittency right, but building the field such that the dissipation is on prescribed sheets that we put in, okay? But we're going to be better in a few years. So that was just to advertise some of my work. This is a list of textbooks on turbulence, where you will find some things which more developments on the things at your will. Landau, GISM, fluid mechanics, Tenex and Lumley, the Frisch of turbulence, which is developing all these things. And Monin-Diaglom has all you want to know about statistical fluid mechanics. It's very technical, but very complete. Priest is a very pedagogical book on magnetic reconnection, so I advise you to read it if you're interested in that. And Goedbloed and Keppens is one of the best books I know of about MHD. So I think this closes the first part. Yeah, okay. That's the 4/5 law, but I'm going to skip that. And so in summary, this is what we know on turbulence. Power spectrum, one analytical results which tells you that the third order structure function behaves like -4/5 epsilon times L, okay? Which tells you this minus sign tells you that it's direct energy transfer towards the small scales. The log normal property of epsilon. All these don't know exactly what coherent structures are, and that's, I think, at least that's my area of research now, and that's why I'm going to tell you about shocks in the next part. So I'm going to take questions.
Yeah, thank you, Pierre, for this introduction. So are there any questions in the audience? So students first. Yeah, please.
Seems like
no, that's me.
Oh,
I think.
Seems like lower temperature phases like CNM has higher Reynolds number, but if I just look at the equation, it seems like it's delta U times L, which means like the hotter phases will have higher numbers. Could you explain why they are?
So that's a good point. This has to do with the density, which controls the viscosity. You mean you're referring to this table I put at the beginning, right? Yeah, so it's just the viscosity. Delta UL is actually almost, well, it's not constant, but it's, so you have to keep this in mind. This is delta U versus L. And now you want to know why the Reynolds number here is very large. And this is because you divide delta UL by the viscosity. And the viscosity is the sound speed times the mean free path. And the mean free path will get very small at large densities. So this is why the Reynolds number is much larger for Coulter phases. It's because they are denser, mainly. Because the velocity is not changing that much with scale. It's just the scaling that I showed. Yeah. And maybe I should add a comment to this, which is I didn't tell about multi-phase turbulence, but this is very important for a priori. I mean, we believe that's very important for our galaxy, and almost nobody works on it. Hopefully, Benjamin will make a breakthrough on this.
Other questions? Okay. Can we go to the second part?
That's one question here.
I'm sorry, it's just about the transfer on the large scale in 2D. Is there, I don't know, how can you connect the fact that in 3D it goes in one way? And if you zoom out at some point, so it should go in the other way because we switch from a 3D environment to a 2D environment. Has it been done in some kind of simulation to look at this zoom and see a 3D transfer, and then you zoom out and you see a 2D transfer?
So several answers. First one, what makes the energy go the other way is the absence of the stretching mechanism in 3D. In 3D, you stretch your vortices, and this makes them much smaller, and energy goes towards the small scales. But you don't have this in 2D. You cannot stretch the vortices. And so I'm lost now. What did you say just before? I had something else to say. Yes, there are numerical simulations which try several aspect ratio of boxes, and they show how to transition from the 3D behavior to the 2D behavior, basically. And this is Alexakis and his student. As a large, yes.
So I'm noticing here on the table that as you go to smaller scales, you find situations in which the viscosity is higher than the diffusivity. So what happens then when your magnetic Reynolds number is smaller than your Reynolds number?
So that's the large. You mean to go from the large PM?
You have a Prandtl number near
exactly.
1, and then you have.
In most of the ISM, in the diffuse part, the Prandtl number is very large, but it's the reverse in the stars, basically. Yeah, and next to the stars in solar physics.
So is there a difference in how turbulence behaves?
So probably. So in MHD, you now have two scales to dissipate. You can dissipate kinetic energy and you can dissipate magnetic fields. And these two scales are separated if your Prandtl number is either very large or very small, and they're not in the same direction. So Alex Chekoshin at the time devised theories on which, I mean, you could not, in some cases, you could not tangle the magnetic field because your velocity is too smooth at these scales. So I think this has now been checked in simulations, but I think the status is still that you just need a large Reynolds number to get good turbulence, to get developed turbulence, and you need both of them, RE large and RM large, to get real developed turbulence. But probably the topology of the structures you would get, depending on the Prandtl number, could be different, or maybe not. I don't know.
Maybe the dissipative structures.
The dissipative structures
will probably be different once you.
Yeah, I'm saying this, and then I'm thinking of my own simulations in which we've varied the Prandtl number, and we find exactly the same, but the same initial conditions. Vary the Prandtl number, we find exactly the same dissipative structures, except their inner structure is different. Okay.
Okay, we should talk more about that.
And the intermittency exponents are blind to. They know, they are telling you things about, at the same time, the inner structures of these dissipative structures and how they are arranged with respect to one another, whereas they are fractal with our. It's a collection of, but it's a very degenerate view, in fact.
So you spoke about galaxies, and you said that view from the external, they can be viewed as 2D.
So if you look at them at scales larger than the scale height, they can be viewed as 2D, and probably energy goes towards larger scales.
Are there? Do you know of any proof of this?
Any
observational proof of this?
No. Spiral arms, maybe? I don't know.
And then that's the question that is reversed to the one. So how do you go from this 2D to 3D when you're looking at one GMC? You have 2D turbulence.
Yes.
Let's say that you have 2D turbulence.
How do they connect?
Yes.
I don't know. It's the same problem in atmospheric. We know meteorologists look at the Earth. It's a 2D fluid from far above, and then when you look at scales smaller than the scale height of the atmosphere, it starts to be 3D. And so the 2D fluid knows. I mean, you can smooth your field and coarse grain it and find properties which are generic properties which come from the smaller scales. And maybe these generic properties will be from 3D turbulence when you look at them. If your smoothing scale is on the order of the scale height.
Yes, and finally, there is a recurring questions where at which scales is coming the energy from turbulence? Is the energy
Okay.
is
So-
injected? And so my question is this has any impact, the scale at which it happens has any impact on the power spectrum?
You have an injection scale,
Yes.
and then you have some power spectrum above it if it's 2D, below it if it's 3D or 2D. Okay. You generate.
That's not exactly my question. My question is, you're injecting the energy at one scale. Does
Yes.
it change the property of the power spectrum at this scale?
At this scale?
Yes.
Yes, usually when you do it in simulations, you get a spike. But simulations, there's a problem of the driving. The driving is artificial in our simulations.
Yes.
I don't think that you can call this driving. I mean, nature doesn't drive turbulence. It's just our ignorance of the process which starts these fluctuations, which we call driving in our simulations. So when we do driving, we do it at a very narrow scale range, and this usually affects the power spectrum. You see a spike in 2D. In 3D, I rarely see a spike. The power spectrum is smooth from the injection scale and goes down. And I know there are also uncertainties because if you can generate in 3D, even you can drive at a given scale and you look at the power spectrum above it, and people don't know whether it's k square or k to the 4. And so there are experiments trying to find out in which case you would get either of the scalings. And I will speak again on the injection in the galaxy at the beginning of the next part.
No more questions?
Oh, okay, I'm lost now in my presentation. Okay. So the second part is now on shock waves. I will link it to the turbulence in the introduction, but just to mention, this is coming essentially from another summer school I did in 2022, and so with the help of all these people. Okay, this is a shock around a supersonic plane. It's a very cool picture. So I'm going to tell a few things now about the turbulence injection problem. I will finally introduce you to the hydrodynamics equations, fluid dynamics equations. We will speak about waves and how they can generate shocks. And then we will look at various aspects of shocks. Hopefully, I'll get to the end. We'll see. Maybe I should just resume this. No, how do I do this? Excellent. Let's get started. So the matter cycle in the galaxy, again, I think you will see this picture a lot in this, although Benjamin managed to skip it, I think. Congratulations, Benjamin. So now we have the same picture, and I've just put a star where you have shocks intervening. So first in the collapse, you form a star, material is falling on the star. You have an accretion shock on that star. That's where the first type of shock. When a supernova explodes, that's a big shock going away from the star into the medium. At the beginning of the formation of a star, you have a jet which launches and outflows and cavities which are surrounded by shocks. You have inner shocks in these jets. The winds launched by stars also have a termination shocks. And finally, you can imagine that these clouds, which are made from the cooling of the hot gas, when they find each other, they also generate shocks. So I want to start by looking at some aspects I've neglected in the previous part, which is in our galaxy, what generates the turbulence? Where is the injection scale precisely? And what is the injection process? And so I compiled this, so maybe half or 100% of it is wrong. But I just want you to see that we don't understand really how turbulence is driven in the galaxies, and almost at all these things, not quite all, but almost all, you get the shocks appear. So precisely not in this one, but that's how it is. So one first idea to generate turbulence was differential rotation. So in our galaxy, we are at about 8 kiloparsec, the sun, and we rotate at 250 kilometers per second. If we imagine that inner the sun, we have a linear gradient, then this means over 100 parsec, I'm going to consider a scale height of 100 parsec, and we are going to consider a cube of 100 parsec around the sun. And let's look at how the turbulence can be driven in that cube. So 100 parsec over this, I computed a delta U of 3 kilometers per second. If I divide by 100 parsec cube, I find my injection rate in CGS to be 8 × 10⁻⁴, compared to 0.1 to 10 from the scaling of Figaro and Eta in 2009. Okay. So that's not enough. Gravitational energy injection, these cloud shocks. So how are they generated? By probably virialization of the clouds with respect to one another. So if we apply the virial theorem to these clouds, let's say that the kinetic energy is on the order of the potential energy. That's factor of 2, but who cares? Then I found that the estimate for the relative velocity between these clouds should be on order of 6.5 kilometers per second. And so I divide this to the cube by L, and I find 10⁻⁴, which doesn't make sense because the previous one was lower. So, okay, so that's a mistake. Exercise, find what's the real value here or the real value here. Next one, turbulence injection in outflows. When a star is born, it accretes material on it, but not all of it falls onto the star, and a jet forms, presumably to get rid of the angular momentum to allow material to come onto the star. And we estimate that about 10% of the stellar material is going to be ejected back into the ISM. Let's assume that it's going to be ejected so with a velocity of 30 kilometers per second. And we need, so that's the energy will be this square times 10% of the stellar mass. And so I need an estimate of the mass of gas in my galaxy first to get the star formation rate within my 100 parsec cube. So I find that I need to divide this by 3 × 10⁴. What do I do next? Yes, and now I need to, this is the total energy injected to this gas. And so I need to, this pi is actually the specific energy transfer rate. So I need to divide by the mass of 100 parsec cube piece of gas and a density of 1 particle per cubic centimeter in the units of the ISM, which you probably know. Instead of CGS, we use parsec, solar mass, and megayear. Okay, that's the ISM unit. So 1 particle per cubic centimeter is 1 solar mass around. It's not exactly equal, but it makes it convenient. 1 solar mass per parsec cube. So that means I have 10⁶ solar mass in my cube, and this divides the energy injection rate I found this way. And I find a very small pi, but I probably made errors. You're gonna find them, I'm sure, before the end of the 2 weeks. energy injection in stellar winds. One easy way to compute what these winds are doing is to look at the momentum injection rate in radiation. This is L over C, all the photons which are emitted by this star. And it's a fraction of these photons, probably 1%, maybe 10% in some cases. This is what launches the winds, okay? So using a 10% gas mass fraction and an L over M ratio of 4 for the star versus mass, stellar luminosity versus mass and 10% gas mass fraction. Then I get a tenth of a solar luminosity divided by C for the momentum injection rate for my 10 to the 6 solar mass piece of gas. So that means I have delta U over T, and I find pi, so R is the 100 parsec. And once you have this and the length scale, there's only one way to build an energy injection rate, and that's this one. So I find also a very small injection rate. Maybe this is completely wrong, but you'll tell me. And the last one, which is the highest, is the turbulence injection in supernovae. So that's a bit easier. So let's do it for type 1a supernovae. Type 1a supernova is a 1.4 solar mass, a Chandrasekhar white dwarf, which has so the mass of a single atom of carbon, that's the number of carbon atoms, and each one of them releases, during the thermal nuclear explosion, releases 8 mega electron volt. That's the difference between the linking energy of the carbon and the linking energy of nickel or cobalt, I don't remember. So you get that amount of energy available by exploding your star. You take 10% of it, which is usually launched into kinetic energy. So you get 10 to the 50 ergs per supernova. At 100 parsec, this 10 to the 50 erg with our average density will give us 4 kilometers per second only. And we have about 1 type 1a per 100 years, but we also have 3 type 2s for 1 type 1a. So let's say 1 supernova every 25 years per galaxy. And this, I then put it to my 100 parsec cubes. So there's this 3 10 to the 4 ratio. I get this rate, which is the highest of all the injection rates I considered, but which is still way below what we need to explain this. So I think there's a problem. I'm sure it's being discussed in the literature. I don't know the solution. You'll tell me. So let's look at shocks now. This is the end of turbulence, and this is a termination shock. So there's a zeta off is launching a wind, we think. And this is the shock between the star and its surrounding medium. So shocks are ubiquitous in the interstellar medium. What they do is to convert ordered energy, kinetic energy of motion, magnetic energy, to degrade it into thermal energy, and that thermal energy serves to excite molecules, sometimes make new molecules. And these molecules we can see and probe. And this is why they are very good probes of the ISM dynamics. And so, and also they are a dust factory because they can break grains and they can make new ones. So they are a very important piece of evidence for the dynamics of the ISM. So we don't really know these things, how much mass, momentum, energy is processed through interstellar shocks. So they are very useful tools, and that's why I'm teaching them now. So hydrodynamics, and I have to be, no, it's fine, I think. I'm on time. So there's nothing more in hydrodynamics than conservation of some quantities: mass, momentum, energy, magnetic fields, okay? And what is important is flows and fluxes. So fluxes is a given quantity per time per unit surface. For instance, mass flux is the density times the velocity. So mass flux through a given surface is the density times the velocity relative to that surface. So let's assume that the surface is fixed. Then it's the orthogonal, the parallel, the orthogonal component of the velocity with respect to that surface. So radiative flux, pressure, radiative flux and pressure are also fluxes of energy here and momentum here. And flows. So this quantity divided by time. So let's do it for mass in details, and then we'll be done for the rest of the things. So time variation of a given quantity in a volume plus the integral of the flux of Q going out of that surface. This is the conservation of a quantity inside a control volume, which can have this whatever shape you want. Let's say it's fixed in space so that the relative velocity between the fluid and that thing is just the velocity of the fluid. So it's easier. So for mass, for instance, it's just this. The time derivative of the total mass in this is just the flux, the integral of rho u around that surface. You can manipulate this until you get to this volume integral where you have used Ostrogradsky to put the surface integral as a divergence of the flux inside. And so that's why all the fluid dynamics equation takes this form. Time derivative of a conserved quantity plus divergence of the flux of that quantity equals to 0. For instance, if you look at the isothermal ideal MHD equations, you have this shape, and it's not easy to see that this J cross B is actually also the divergence of some kind of flux. I'm using Einstein convention here. Jj is the implicit summation of over J's. But all these things are really in this form. The time derivative of a conserved quantity is the divergence of a flux. Okay, and this is a complicated function, but who cares? This is just the mathematical expression of conservation of some quantities in MHD, rho, the momentum vector, and the magnetic vector. If you have non-ideal now MHD equations, it's still the same. It's just that you add components to the fluxes, one viscous flux here, one ambipolar flux here, and one resistive flux here. And I think so these equations pretty much summarize, I think every, you could use these equations for the behavior of almost, well, no, you would have to add energy and energy conservation and cooling. But for isothermal fluids, for a phase of the ISM, which is of constant temperature, say, whether that exists, I'm not sure. But these are the equations you should use. And they are also of that shape. Time derivative of a conserved quantity plus the divergence of a flux. Now, the flux is not only a function of the conserved quantities, it's also a function of the gradient of these quantities through the diffusive fluxes. And I can now go to the waves very briefly. So the definition of a planar wave is just something which moves without changing. So for all the variables which characterize the fluid, they take the shape x minus ct, where c is a constant or a local constant, at which this thing is moving without changing. Okay, this is just expressing that in time, the shape, the profile of something, of the characteristic variables of your gas are moving at a constant speed c. Okay, so That's why we say plane waves carry information at speed c. If you have a small perturbation somewhere, they will carry it at the speed c. So let's investigate what kind of waves are allowed by our equations here. We simply plug that into the fluid dynamics equation, and we obtain minus c. So we assume that we are in a 1D world. I mean, every locally, the variables change only in one direction, which we call x, okay? This is planar waves. They are defined, they have equal quantities on planes. So we obtain this equation, and this equation on the gradient of the state variables is simply an defining C as the eigenvalue of that matrix, which is the Jacobian of the flux of the variables, times the gradient. Okay. A matrix times this vector equals C times this vector. So this vector is an eigenvector of this matrix associated to the eigenvalues C. So this is the way to find all the waves, okay, which one type of fluid can have. We also say that the system is hyperbolic when all eigenvalues are different. And I also note that very often you can find an orthogonal basis of these eigenvectors, which makes it very nice to decompose a given feature. And then we know exactly how each of these components are going to be transported. Okay, each one is going to be transported at its own eigenvalue, its own wave speed. Okay. I will skip that. So just for those who are more familiar with a small perturbations approach, okay, assume a homogeneous background, the small perturbation W1. What you've been used to see is that the perturbation is simply taking the form of a planar wave, an exponential of a complex phase here. And if you plug this into that equation, you will recognize the same equation as before by just applying this transformation. Okay. So now you're back to probably things that you knew before, but I find the other approach quite nice and sometimes enlightening. So for barotropic hydrodynamics, I can do this derivation on the blackboard for those who want later, but you find three waves. One wave, so three eigenvalues and three eigenvectors. One is transporting the shear, so the difference in transverse velocity along the wave propagation direction at the speed of the fluid. And the other two are sound waves, and they propagate perturbation of density with either towards the right, plus with a plus sign, or towards the left. Okay, so this in the position time diagram, a perturbation here, which is decomposed into a gradient of rho and u shear extra, will give rise to these three perturbations, three components being propagated this way. Now, if you take a compression wave, let's say you have a linear wave, so very small amplitude, a sinusoidal shape of the velocity along x, then this thing will propagate at let's say the speed of this perturbation is c. This thing is c plus du, and this thing will propagate with c minus du, while this propagates as c. Okay. So this means this bump will catch up with this one. As time evolves, if we now keep our frame close to that wave, what will happen is that the bump before will catch up with the one after. And at some point, they will arrive at the same place. And then we have a jump in the quantities, okay? There's no other way to resolve this, this contradiction by having a jump into the fluid. So why the sound I'm emitting now is not steepening progressively and making a shock into your ears? This is because the time it takes for this to happen is on the order of L. So it's a quarter of L divided by du if you do the geometrical diagram to see when the first bump will catch the two bumps will catch up with each other. So that means the time scale you need for this to happen is C over delta U, okay? So that means if your wave is linear, the steepening will happen in a lot of crossing time, okay? The waves that maybe are emitting, their amplitude is so small compared to I'm very far from making a big bang, a sound bang, and so there's no way this is steepening before it reaches your ears, okay? The wave will damp before this happens. But if the velocity is on the order of the sound speed, if your Mach number is around 1, then this will happen very quickly, okay? The wave will cross only one time its periodic length, and you will have shell crossing. So this is an experiment in a swimming pool when they didn't know that the sea exists, and they launch waves and they look at the steepening on the waves. But this is exactly what is happening. There is the bottom of this is I'm not sure it's flat or slanted though. But the height of the wave is on the order of the depth, okay? And so we are in the case where, because the depth is controlling the wave speed in surface waves, and so that means that the steepening will happen very quickly, okay? So I hope you know you're not looking at the waves at the sea, you're looking at the steepening of a surface wave, okay? So let's go back to this sketch, and let's assume that you have two perturbations. One which has, and we are in a compressive case where the guy on the left is moving faster than the guy on the right. And so this means that these things will cross at a given time. And if the sound speed is constant, okay, then these things will happen exactly at the same time. So in fact, this steepening will give rise to 3 different kinds of discontinuities. Here you will have a discontinuity in the transverse velocity, because this is how the transverse perturbations move. And here you will get 2 discontinuities in density. So what happens is when you start a perturbation in velocity, you cannot do something else than producing 2 shocks back to back and in between a shear wave. So that I discovered recently, and I haven't published yet, but I think it's an interesting fact. So here you have a 2D simulation where I just initiate perturbation velocities at the beginning, and I see shock evolving. And if I'm looking slowly, snapshots by snapshot, at how these shocks are forming, you see that this is a pressure jumps, and so this means there's 1 shock here and 1 shock just here. So these shocks are really appearing back to back, and I can predict from the initial velocity field where they are going to be produced. And not only that, but if I look at the compressive, so the divergence of U particle, so the shearing, the curl of U square, and I color green is curl of U square, and blue is divergence of U square. So blue is where there is compression, where there is a shock. Green is where there is shear, where there is a shearing sheet. And you see that there is green in between the blues. So it's really exactly that thing which is predicted by this picture. Okay. Finally, we have a shock. And now we are looking at what constrains one side of the shock to the other side of the shock. So we assume that the shock is steady state. And so we use a control volume in the frame of that steady state shock, which has this shape. It's still the same equation. And we're just integrating that control over that control volume in this equation. And so what we find is that the value of the flux here needs to be equal to the value of the flux here. Okay. When you put this just on either side of the sheet of the working surface. So basically, these are the Rankine-Hugoniot equations, and what they do is they link the fluxes of mass, momentum, energy, magnetic field on either side of the shock. So you just write the series of equations, and then you have what is called the Rankine-Hugoniot constraints of a steady state discontinuity, whatever that is. It could be a shock, it could be something else. We'll see that these Rankine-Hugoniot discontinuities or steady state discontinuities, they can be classified in several families. One of them is shocks, but not only shocks. From these equations, you can link then the conditions on one side to the conditions on the other side. And for example, you can compute the compression, the ratio of the density entrance versus exit. And you can see that in an isothermal shock, the compression factor will be proportional to the square of the Mach, equal to the square of the Mach at large Mach number. Mach being the entrance velocity divided by the sound speed. Should have defined this before. Another important property is that the max temperature, so this comes from energy conservation. You can derive from these equations, or rather plus the energy conservation one, which I failed to write down here. You can see that the max temperature will scale as the the square of the shock, and a nice rule of thumb is to use this with the molecular weight of the ISM. The max temperature just behind the adiabatic shock front is going to be 53K times U to the square in kilometers per second. So that's an easy way to find out what kind of temperature you get behind, whether you will be able to reach some energetic barriers for chemistry, as Benjamin showed you before, and perhaps or destroying molecules such as H2 molecules. So the classification of MHD discontinuities, you can look at the normal velocity to the shock, how if it's not changing and if the density is not changing, it's a bit boring. But if the density is changing and the velocity is not, then we are in the families of contact discontinuities. If the normal velocity is changing, but the density is not, then we are in rotational discontinuities. We have the magnetic field changes direction, and that's all that happens. And the transverse velocity changes as well. That's another thing. And shocks are whenever the normal velocity changes and the density changes. So this I will skip. So now we have linked the quantities on one side of the shock, the pre-shock, say, to the post-shock quantities. What happens in between? This is where we are interested. We want to know how the temperature behaves. Maybe we want to know how the chemistry changes. We want to know how the velocity changes. Maybe we want to produce lines out of this. And so we need to understand what smoothes the discontinuity. So we have three processes, three diffusive and dissipative processes. So the first one is viscous dissipation. So it's transfer of momentum through collisions between the particles. So the viscosity is the mean free path times the thermal velocity. And you can build a viscous pressure out of this, which is 4/3 if you are in the normal direction, 1 if not. Rho times the viscosity times the derivative of the velocity. And from this, you can find a nice proxy for the physical length of the width of the adiabatic shock front. And this is the viscosity value divided by the entrance velocity. So the faster the shock, the thinner the dissipation front. And the more viscous, the larger, but that's more to be expected. Another kind of diffusion is the ambipolar diffusion. So you have two cases. I think the ambipolar diffusion case is more often at work in the ISM, but let's start with two fluids. So you have two fluids. One is charged and fills the magnetic field. It has talkie-walkies to warn the others that something is happening. The other is simply neutrals. They have to collide to pass the information. And so there's probably a velocity difference between those two fluids because one feels the magnetic fields, the other doesn't. So there's a systematic velocity between the two, and there's a drag between those two fluids. The ions will recouple to the neutrals when they have exchanged enough momentum by collisions. And classically, we use this momentum transfer cross-section for ISM gases. Ambipolar diffusion assumes that the ion inertia is negligible, which means that we can equate the Lorentz force to the drag force. And this means we can get rid of the equation which follows the dynamics of the ions. And we can just plug so the neutrals, they feel only the drag of the ion, but since this drag is J cross B, the Lorentz force, now the neutrals start to feel the Lorentz force, okay? And this is the classical MHD equations are usually like this. You feel it's an equation for, you can view it either as an equation for the neutrals, and then you add ambipolar diffusion in the induction equation, or you can you view it as an equation for the global fluid, and then J cross B just appears in the equation. And the last bit of diffusivity, which you will encounter in the interstellar medium, is the resistivity. So resistivity is defined by how the electric field relates to the current. Okay, so let's go this way. We imagine that there is an electric field, and we'll see what it does to the current. So an electron is moving through this fluid and feels an electric field. In between two collisions of neutral, it will acquire an impulsion, a momentum of me times u, the velocity it will get by the acceleration of the electric field during tau, which is the collision time between two neutrals, or it could be ions. It depends on how the fluid is charged or not. So the resistivity is and then the charge drift current is the the number of electrons times that velocity, which has been acquired by the electrons with respect to the rest of the fluid. So if you now take the ratio between those two, you have MEU divided by NE, and I forgot the tau. Well, you get this. And then tau, you can express it as the mean free path divided by the thermal velocity. And so you get the resistivity this way. And this is a simplified expression which applies in a large range of cases in the ASM. And that's how, by the way, I built my table of Reynolds number and magnetic Reynolds numbers at the beginning. So now we have all the tools to build the internal shock structures. But just before I start this, so these are equations with now the resistive stresses or viscous stresses, the dissipation stresses. And so finally, the equation in a steady frame where the partial derivative versus time is 0 is simply saying that along the profile, the distance across the shock, this flux has to stay constant. So this is another way to write the steady state equations of the shock. And you can see that the profile of the shock is parameterized by the conserved fluxes. And since you can build all these conserved fluxes from, say, the parameters in entrance, then the profile of the shock depends on the entrance parameters. So I'm going to give a few examples of time-dependent shocks before I delve into the steady ones. These are, for instance, the equations of a time-dependent shock with not necessarily a shock, but fluid dynamics, 1D fluid dynamics with chemistry, with the momentum exchange, two fluids, neutrals and charges, cooling, drag between drag between the neutrals and charges, heat exchanges from collisions between the ions and neutrals, between the electrons and neutrals, etc. And magnetic field conservation. So this is a bit hard to solve. It takes hours to compute, but it's doable. This is what I used to do in my PhD. And if you look at the energy equation now alone, and you look at it in steady state, so we will cross this over, the energy is shared between thermal energy, internal energy, so the sum of all the excited, how many particles are in such excited levels, the kinetic energy and the magnetic energy. And you have the fluxes of energy, which is a bit complicated. That's why I decided to put this equation separately from all the others. Now you can access the energy radiated by just computing the difference of this flux on one side versus the other of the shock, which will be a fraction of this entrance energy, which is usually dominating the energy, the energy flux, sorry, U times half of rho U square, which is half of rho U cube. So if you look at how this energy flux is varying across the shock, you see that we start with kinetic energy, we transfer energy to viscous energy, then viscous energy is transferred to thermal energy. And now that we are hot, we can excite the molecules and we get some internal energy, which is radiated away. And along this path, the magnetic field is compressed and enhanced. This point where we have reached the conversion of kinetic energy into thermal through viscous dissipation is called the adiabatic front. And behind it, we call it the relaxation layer, where the temperature we've reached is going to affect the chemistry, affect how the molecules react to this, and affect the diagnostics we can get from our telescopes. So here are some examples of time-dependent profiles. I'm not sure I want to late now. Let's keep this. So in two fluids MHD, we have charges and neutrals. We have basically two velocities, the Alfvén speed here and the fast speed, which is usually the Alfvén speed is slow compared to the fast speed, and really slow if the ion density is small compared to the neutral density, because the Alfvén speed behaves as 1/square root of the density. So if we have just a small amount of charges, then the fast speed is really, really fast, okay? And that's the case of the interstellar medium. So there's plenty of room here to have shocks for which the velocity is below this, but larger than this. And this is what we call C-type shocks. But we start with J-type shocks, where the speed is larger than both these values, okay? So this is a jump shock. And here you see the temperature rising very fast to that value I was telling you about, the 53 times U square in kilometers per second. And then you relax down to a temperature which is close to the original temperature in the relaxation layer. If the velocity is in between the fast ion speed and the Alfvén speed, then you get continuous types of shocks where the temperature doesn't rise as much, but the distance here, which is 3 × 10⁻³ is much larger than the distance here, 10⁻. This is 1 AU almost. So we have now something which doesn't heat as much, but does it for way larger distances. And these types of shocks, therefore, do affect very differently the chemistry of the ASM. You have intermediate things, and the C-type shocks, when it's steady in its early days, has a jump, and these are the first simulations of C-type shocks. It was a paper in '98, which show how you go from having a jump in the neutrals to no jump at all, but maybe that's not so interesting for you now. So let's look at shock stability. Now this, or maybe I will skip all this because I want to let you have questions. So you can ask me later if you need details. I want to talk a bit about the Paris-Durham shock code, which is a shock code designed for the ASM for molecular shocks. That is shocks with molecules in them. And right now, it's limited to 40 kilometers per second, between 0 and 40 kilometers per second, or maybe between a few, because you need to be supersonic still. So this is a code born from a collaboration between David Flower and Guillaume Pinot-Desforêts. It dwells with so the conservation equation I showed you with a devote solver, and it can accept a large chemical networks, lots of lines of H2, and the main developer today is Benjamin. And you'll find it on at this URL if you want to play with it. It has several branches. Some of them include dust physics and collisions, stellar winds, disk winds, and Benjamin is now making sure that the code can progress into the realm of self-irradiated shocks. So you should check the coming papers. And I also did an interface of this shock code with a simplified version of Ramses, which is called Doomsys. So I showed you this slide of time-dependent equations for the shock. Now we are going to look at steady shocks. It's way simpler, which just have a system of ordinary differential equations, which we solve by on-the-shelf methods. You can read this if you're interested. I've already placed this slide. I just want to speak a bit about the heating and cooling processes, which are currently in the public version of the code. Knowing that we are now, I mean, Benjamin is developing higher, better versions of this cooling to be able to reach pretty much the conditions of mappings, but this is not ready yet. So the chemistry is very versatile. You give it as an input file, which you can change by hand. You can grab your chemical equations from the KIDA base if you want, or you can use the one that Benjamin carefully put together with Guillaume. It can handle 2-body or 3-body reactions, photo reactions, cosmic ray induced, grain surface, catalyzed reaction only for H2 and HD formation right now. It has some capabilities, not in all versions, but of thermal desorption, but mental sputtering, core erosion, and photo desorption. No, not for photo desorption yet, I think. This is not in the public version, but all the rest is in the public version. It does some of the line emissions, and Benjamin and Antoine have been developing post-processing tools to get the line emission rates. And I want to now go to how to do more than 1D shocks by using 1D steady shocks. So radiated shocks, this is Benjamin's business, grain physics. Yes, I want to spend some time on this. So this is a slide I showed you before in the previous part. These are Rankine-Hugoniot discontinuities that we detected in a 3D MHD simulation. 3D MHD, so if you remember, the Rankine-Hugoniot conditions are, we need to be steady state, we need to be planar, and we need to be homogeneous before and after. So this is a lot, but it seems to hold in MHD simulation. It turns out that in MHD, the dissipative structures are mainly sheet-like, okay? And so on the local piece of such a sheet, you can try to verify whether Rankine-Hugoniot holds, and it does hold, okay? So we can, since it does hold, we can put these Rankine-Hugoniot discontinuities in several families: fast shocks, slow shocks, Parker sheets, rotational discontinuities. We still have 20% of unidentified things, but most of these things are identifiable. Some of them are shocks, and we could imagine to model each piece of this shock with a 1D steady shock then, and recover what would be its emission and its chemical yields from the Paris-Duran shock code, for instance. All we need to do is to compute the statistics. We need to know how many of shocks with entrance conditions, 1 kilometers per second, 3 kilometers per second, etc. Once we have the statistics of the shocks, we can build again the yields from the molecules. And that's what I did in a recent paper with 2D hydro, so no magnetic fields, but 2D hydro turbulence. I just shake a piece of fluid with the chemistry, so complicated numerical computation with chemistry and hydro-coupled. And then I check that I can recover the complicated simulation with a collection of 1D shocks. And this seems to work quite well. But 2D without B field, maybe it's another story with B field. So why not apply these kind of things to bow shocks, for which we know the shape and we know exactly the entrance velocity in each part of that shape. So that was done by Christensen et al. Here and Gustafsson et al. In 2010, where they tried to model the shape of a bow shock by applying several pieces of 1D shocks, and they succeeded into interpreting observations this way. Using the same kind of, so this is the model behind it. You have an ambient flow which enters a prescribed shape, and you know the entrance velocity of that shock is simply the orthogonal component of that velocity entering here. So you can know from just specifying the shape here, you know exactly the statistics of the entrance velocities in the shock. If you have a magnetic field as well, you can even know the statistics of the B field inside the shock. So you can build from a grid of model, of 1D steady state model, you can build the line profile and emission and rotational diagrams coming from these bow shocks. So here, what Chan did in his PhD, so this is first the observations on a 1D shock model, a planar model done by at the time 2015 to the best fit of this model, so similar to what Benjamin showed for this morning, excitation diagram and what the model predicts. It's a bit further away, but still it's a 1D model, so quite impressive. But you can do better by adding just 2 parameters, which are the angle with which we see that bow shock and the angle, the strength of the angle of the magnetic field with respect to the nose of the bow shock. And so from just the rotational diagram, you can access geometrical properties of the bow shock. So this was a very neat thing. We also did through now not only the rotational diagrams, but through the line profiles, Cham was able to derive some of the properties of another bow shock. So maybe I won't spend too much time on this, but basically using collections of 1D shocks can access geometrical properties of the shock. So I think I will stop here to get some questions. The summary, the take-home message of this part is that waves, linear waves, compressive linear waves always stiffen and we form shocks, okay? They are very common. You can, with the Rankine-Lagrange conditions, you link pre-shock and post-shock conditions. Knowing your dissipative process within the shock, you can know the profile of the shocks within that thin structure where the kinetic energy is dissipated. And then you can recover very fine diagnostics of these shocks and try to access the dynamics of the interstellar medium from observational properties. And I think I should stop here.
So, are there questions, especially from students?
Thank you for lecture. So I just, well, this like you can judge whether the question makes sense. So you said that in the first part of this lecture, you said the real driving of the turbulence is unknown in our galaxy, or like we have different components.
I can't make sense. I can't make sense of the injection rate of the
injection
turbulence.
rate,
Yeah.
right? So if you set up a molecular cloud with some turbulence driving, and what is that a free parameter, or do you don't use that as a free parameter? You
In a
somehow avoid that
simulation,
problem.
yeah, in the simulation, you would set up your driving so that you get the observational outcome. You get the velocities.
Right. So that is a free parameter.
So that's a free. The driving is then reflecting your ignorance on what actually is injecting energy into these random motions. And you can with the in a simulation, a driven simulation, you can you have a handle and you can decide how much power you put in, but you don't say which process is making it. So on the other hand, there are simulations, global simulations of the galaxy, which treat supernovae, which have the rotational shear of the galaxy. So when I did this, I started to write this lecture, and I was thinking I'm gonna find which rate is correct. And I was expecting to not being able to distinguish between the rates, that they would all give me the proper solution. But they all seem to fall short. So I must have made a mistake. Because simulations of global galaxies, they actually, I mean, the Milky Way simulations of galaxies, I don't think they have a problem to find out the actual properties of the galaxy. Or maybe I'm mistaken. I mean, I'm not an expert on this, but they do.
Okay, thank you.
Yeah, sorry, I probably confused you with this.
So I'm looking at this slide, I think 106, which is about energy fluxes through a steady shock.
Yes.
I couldn't make sense of the x-axis. So it says time in years. And
it says what? This is for
almost there.
Yeah.
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 Oh, sorry. The next one, I think.
Ah,
the graph.
Yes.
Yes. So I couldn't make sense of this. So is it saying that in a steady shock, as time passes, the flux changes from kinetic to thermal, but on the order of 1 year, or?
Yeah. Thanks to bring that out, because I didn't have time to. Okay. In a steady shock, you have a given shape which moves in space without changing. Okay. But you can also consider yourself to be a fluid particle, and you put yourself in the frame of that shock moving. Okay. And now fluid particles are moving, and they go inside the shock front. They are being heated, and then they cool down, and they reach the post shock. Okay. And so this is the flow time that I'm looking at. This is the time at time t equals 0, I enter the shock. I am a fluid particle. I get heated, and this takes time. I get viscously frictioned. I get thermally heated. I get excited, and then I get compressed, and this way I build up magnetic fields.
Okay.
Is it?
Yeah.
Did I answer then? Yeah.
Yeah.
No.
And one follow-up question is, if you consider a very simple system of a OB star pushing out its radiation in a symmetrical way, and maybe it's surrounded by PDRs, how would you think of this particle going? So what kind of shocks would you expect? And does this, how would you make sense of this time scale there?
Okay, so then you would consider a small stamp around, so you have a big bubble which is expanding. It needs to be a planar shock. So take a small stamp so that the bubble is flat on this stamp, okay? And you don't look at times too long so that the geometry of the bubble changes by too much, so that you don't have these curvature problems. And then you can look at this shock during this time interval as being steady, and you can compute the structure of that shock during that time. Okay, so that makes a bit more approximations, I would say, but you should be able to apply steady pieces of steady state shocks to this kind of bubbles.
Hi. Thank you for a very nice lecture. I want to go back to the discussion about the driving source.
Yes.
When you were looking at all these different possibilities, specifically on outflows, I was just struck by how long the time scale you used.
Yes, because my idea was that I take 10% of the stellar mass of the stars which are being formed. I throw them out with a velocity of 30 kilometers per second. And so the time scale is very long because for the galaxy, it's one solar mass per year. And I have only 100 parsec cube of gas. So that means I estimated, but maybe this is wrong, 3×10⁴ less. So that's 3×⁻⁵ solar mass per year in my 100 parsec cube for new stars being formed. And then the total energy coming from the 10% of stellar mass, gas launched at 30 kilometers per second. This I had to divide by the mass of that cube to get the specific rate of injection.
Right. I think it's possible. I guess over such long time scale, star formation rate is not constant. It seems there's a lot of room for adjustments. So especially if the bursty starburst history, not in that too distant past, average over such long time scale, I think the energy injection may be underestimated.
Okay, so that means we would be, if we are following a large rise of star formation, then we would still be in a more turbulent state because we had recently experienced a large injection rate. Okay.
Okay, thank you, Pierre.